Welcome to race podcast number 127, and today we're talking about the second half of this podcast, which is about movable flow control devices on cars, fast cars, and in particular when they're going on straights compared to going around corners. And to do that, we're looking at this paper again called Influence of the Car Movable Aerodynamic Elements on Fast Road Car Cornering. The first part of this podcast, 126, we went through quite a few of these flow control devices, and now in this podcast, we're going to finish off these flow control devices. So let's quickly cover a couple of things that you should probably recall from the last podcast, just in case you forgot them before then. One of them is the gurney flap. So we're going to be recovering that again in this podcast, but in even more depth and under different situations. So the gurney flap, for those of you who don't remember or don't know, is this little flap at the back of airfoils, and typically at the trailing edge, and they will usually flap up in the direction of the suction side. So if you have an airfoil on an airplane, for example, the suction side, on the pressure side, I should say. So they on the airfoil on an airplane, they are down. For a wing on a car, on the spoiler, for example, they are up, pointing up. And for those of you who are just listening to this on Spotify or Google or whatever, you can find the video on Spotify and or YouTube. On YouTube, you'll find some of our other goodies as well. So check that out if you want to see the video of this. And this paper you can find in the link in the description. It's open access. The other thing that we should cover again is the booster plate. So we're talking about in last podcast, the spoiler at the back of the car. But then behind the spoiler, you have like this additional flap that flaps up to help the spoiler work properly, like to work even better, and the car to produce even more downforce, and in particular, some more drag as well. So we're going to be looking at this concept again. So let's move on to this podcast. Now we've covered those two aspects that will pop up again. So let's talk about the effects of a separate wing with a support plate. So just a wing in general with a support plate underneath, this booster plate underneath, and what the effects are of this booster plate on this support, on this regular wing. So increasing the booster plate is beneficial for the downforce produced by the wing, so this angle, up to a certain angle of attack. But as expected, once you push the booster plate to a higher angle of attack, flow separation seems to kick in and around the downforce drops a little, while the drag coefficient increases significantly. So you can see here they tested this wing with and without the booster plate, and the booster plate at 25 degrees and 40 degrees angle attacks. When you go from no support plate, so no booster plate, to a booster plate at 25 degrees, the lift coefficient, or the downforce, I should say, increases by like 25%, so it's pretty good. The drag, though, for some, unfortunately, increases about 50%. Now, if you were to increase the angle of attack of the booster plate even more while keeping the wing angle of attack constant at 15 degrees, the lift coefficient, or the downforce coefficient, actually drops a little bit, so it's not as good. So the booster plate at this angle of attack is actually making the entire setup worse for producing downforce, so it reduces by about almost 5%, let's say. The drag, though, continually increases by about another 25%, or 33% in this case. So we get a continual increase in drag, but after a certain point, the angle of attack, increasing it greater than 25 degrees, for example, reduces the downforce. So that's detrimental. Now, increasing the drag is not necessarily a bad thing, particularly if you're in corners. So in corners, when you're coming into the corner for a car, you want to be able to carry as much speed into the corner as possible. And the only way that you can really do that is if you have a very good braking system. If you have a very good braking system, it means that you can go more into the corner before you start braking, because you can throw off this speed as quickly as possible. It's quite efficient, which means that you can go around the hardest part of the corner without spinning out or losing traction, because you can reduce the speed to a certain amount that you need. So having a lot more drag with increasing angle attacks for the booster plate is quite a good thing, but the downforce drops a little bit. So that's something to be aware of. And the downforce dropping means that you lose traction effectively, and that will reduce how fast you can go around the corner as well. So you need to drop the velocity even more. So moving on, let's look at the wing tilted to one side. We talked about this a little bit in the last podcast, where they actually have a wing on top of the car spoiler, but they tilt it to one side, so it's not flat, like it's not level. It's like shonky. It's one side up is up more than the other. And in figure 20, we can see the geometry of this. So you can see this wing is tilted a lot. This is only a 9-degree tilt, by the way. It's not very much, but it looks a lot more than what it is, I guess. And they have these cars plotted in the pressure coefficient. So these researchers looked also at how adding this tilted rear spoiler to the car affects the car's lateral force. The idea behind this is to provide the car with more lateral force to be able to corner faster instead of relying solely on the force derived from just the car tires. So the lateral, like the cornering traction, comes from the tires, but if you can give a little bit more force in the direction of cornering through aerodynamic flow control devices, that means you can corner faster. So how successful were they with this? So by putting a spoiler at quite an aggressive slant to the side, a considerable amount of side force was generated, so about 234 newtons. This resulted in a side force of side force coefficient, of 0.113, which is quite a lot when you think about it for just one flow control device at 9-degree tilt angle. The wing still produced quite a lot of downforce with a downforce coefficient of 0.48, so that's quite good. However, the drag coefficient was quite high, still being at about 0.445. And interestingly, in figure 20, you can see the pressures plotted on the car with the wing tilted down on one side. There was actually higher pressure being produced on the car's boot or trunk as well. So you can see here in this front view, you have obviously high pressure on the top here of the wing, which is good. That's pushing the car down. But if you look just at the back of the car, you can see one side has a lot higher pressure than the other side. So that's also adding to the downforce as well. So that's quite good. Interestingly, if we look at the diffuser here on the right, it doesn't really seem to be affected much by the tilting of the wing to one side. So you can see that the top part, that was affected, but the diffuser under here, it still has quite a symmetrical pressure distribution. That's a little surprising because diffusers usually are quite sensitive to different changes on the car. But I guess maybe in this particular case, it's too far downstream, this wing, to affect the diffuser. If we have something happening around the hood, for example, that might change enough of the aerodynamics around the car to change the diffuser as well, to make it a little bit asymmetric. But in this particular case, the diffuser is still acting quite symmetrically, so this wing is not affecting the diffuser. Moving on, we can see some cut planes through the rear spoiler with this tilt, and we can see the velocity plots around it. So one of the major problems of the tilted wing can be seen in this figure. If you want to pause the video here and look at it yourself before I go on, do so. Otherwise, we're going to jump straight into what's going on here. So the side of the wing that has a much higher distance from the car, so this right side here, is performing as you'd expect. So you have high velocity underneath because this wing is tilted like reversed. You have the pressure side underneath, which means that the flow underneath that is going, the suction side is underneath, which means that the flow going there is accelerating quite a lot. And you get that as you'd expect. But the side that is very close to the car's boot, so this left side, is now starting to get some interference from the car itself because not enough air can travel under the wing. So it is effectively choking the flow here. You can see that like you have this real low velocity wake, and this is because there's like not enough area for this flow to come under. It's just like choking this flow, so we're getting a larger wake here. What this means is that this wing is not going to be producing as much downforce as what it could be because now you have this pressure, the suction side here, not really performing. So you have a whole bit of this wing not really performing as it should be, so you're going to be producing the entire performance of the wing. I wonder what would happen if you move the entire wing up by about 15 centimeters to allow more air underneath this side of the wing to help it produce more downforce. I think that would probably increase the downforce production and also reduce the drag coefficient because the wake would be smaller here as well. Here, because we have such a low velocity, that's going to be a wake. That's going to be a pressure drag increase. So by elevating this entire wing by 15 centimeters or so, not rechanging the tilt, keep the same tilt angle, but just elevate it higher, I think the wing will be producing a lot more downforce and less drag, which, again, that may not be such a great thing with the drag if you want to increase the drag during cornering. But from what I can tell, this wing doesn't change angle of attack as you go into different corners. So on the straight, you're going to be getting this drag as well, which is not ideal. In addition to this, they also looked at how changing the wing's angle of attack affected its performance. So this wing is still in the exact same configuration, but now they're just increased angle of attack to 14 degrees. The original one was 7 degrees, now it's 14 degrees. For a normal wing, you would expect that the downforce produced at 14 degrees would be almost double that of 7 degrees, depending on the wing and the Reynolds number. And the drag coefficient would be similar still, or maybe a little bit higher for the 14 degree angle of attack case. So for example, a NACA 0020 This is a very simple wing that you can find like tons of information on. And if you were to put this wing at 70-degree angle of attack at this Reynolds number, you'd get about a lift coefficient of about 0.7. If you were to double the angle of attack to 14 degrees, the lift coefficient would be about 1.3, about 1.3. So that's almost double. However, in this situation, doubling the angle of attack from 7 degrees to 14 degrees only increased the downforce coefficient by about 4%. So not like 100%, only 4% is almost no effect. Also, the drag coefficient actually dropped a little bit by about 3%. So for this particular study, this was done with CFD. So these percentages of 4% and 3% probably wouldn't, they're bordering on the error. So they may occur, they may not occur. However, these results definitively show that the wing is quite indifferent to a large changing angle of attack, far more indifferent than an isolated wing and far more indifferent than like a NACA 0020. So these results were obtained for a velocity of about 30 meters per second, which is 110 kilometers per hour. That's quite fast. In this range, the aerodynamic forces of the car are generally the dominant forces acting on the car, with the only other major force being the actual driving force from the engine to the road. So I'm a little bit surprised that increasing angle of attack here in this configuration didn't have much of an effect on the downforce produced. Now note, this is just a regular wing with no gurney flap, no booster plate. We're going to be looking at those a little bit later. Now let's move on first to straightforward driving and aerodynamic braking. So we just talked about changing the wing's angle of attack to small and even moderate angles of attack. But what about extreme angles of attack? So for example, let's say that you want to use the wing to help braking. How do the forces of this tilted wing compare? So the researchers looked into this as well by rotating the wing from 23 degrees to 60 degrees. And it should be noted that the booster plate on these were used and they were pitched at 40-degree angle of attack. So that was constant throughout. They have another one where they had the booster plate at 25 degrees angle of attack. We're not going to look at that. We're going to look at the 40-degree cases because that's more thorough and we can compare them better. So under these configurations of the tilted wing at the back at 9 degrees and this wing is at 23 degrees and 60 degrees and the booster plate is remaining constant at 40 degrees, surprisingly, increasing the angle of attack from 23 degrees to 60 degrees didn't really increase the drag too much. So like it did increase, but only from about 0.68 to 0.73, the drag coefficient. Considering how much greater this angle of attack is, I expect a greater increase in the drag coefficient. Like it's a massive change in angle of attack, and yet the drag coefficient is almost insignificantly affected. However, there may be a clue as to why the drag coefficient didn't increase so much. And this comes from the downforce coefficient. So if we look at the downforce coefficient at 23 degrees angle of attack, it was about 0.51. When we increased the angle of attack to 60 degrees, the downforce coefficient was only 0.5. So it didn't change much at all. So this means that the wing was probably in some sort of stall, I think, for it to be that indifferent to the angle of attack the downforce produced. That's the only thing I can really think of. So this means that regardless of the change, this geometry now is effectively acting as a bluff body. That would explain why we get such a similar drag coefficient at high angles of attack, because we don't really have a streamlined body anymore, and it's quite indifferent to this angle of attack change, and we get this stall pattern. So that would explain that. Now let's look at the forces on the car while cornering. So we've looked at straight line for now and some sort of braking, but let's look at cornering. So this is pretty cool. Actually, I should probably mention how they set this up for those of you who can't remember from last podcast. Let me quickly go back to the CFD setup. So we have the reference point. They looked at a couple of different CFD setups. One of them was actually a curved domain. So we can see here in figure 3 that the car is in this domain and it's curved along as you would with cornering. So now we know what that looks like. Let's go back to what we were just looking at here, the cornering CFD. So first of all, the researchers only had the booster plate present, so no rear wing. They changed the booster plate's angle of attack from 0 degrees up to 50 degrees. And there was also one at 25 degrees. As expected, as you increase the booster plate's angle from 0 degrees to 50 degrees, the drag coefficient rises significantly. This also starts at, the drag coefficient starts at 0.31 and it makes its way all the way up to 0.365. That's a huge increase for such a little plate when you think about it. So remember back to what I showed you, this booster plate is not that big. It's like, I don't know, like size of maybe half a shoebox in height, and then it extends maybe half of the car's back, not very much. So that's a huge increase. A small plate can increase the total drag coefficient of the entire car by only 16% by itself. So this is the entire car now that this booster plate is affecting by this much. So while the increase in drag is impressive, the increase in downforce is even more impressive. So at 0-degree angle attack, the downforce coefficient is 0.06, but at 50 degrees, the downforce coefficient is now 0.245. That's impressive. A small plate on the back of the car increases the downforce of the entire car by 300%. So that shows just how effective these little things are. So after seeing that, the increase in the drag coefficient that I reported earlier isn't really that extreme anymore. This increase by 16% is not that big, considering that you're getting such a big benefit with the downforce production. So that was only this little booster plate. What about cornering with the inverted wing as well? And what about if you tilt the wing to one side compared to the other? So if you have a 9 degrees tilted on one side or 9 degrees to the other side, let's look at those configurations. So in figure 26, this shows these effects. First of all, let's look at when the booster plate is at 0-degree angle attack. At this point, switching the wing from tilted down on one side to the other has a very minor effect on any of the force coefficients. So the drag, the downforce, and the side force coefficients all change, but they're only like 0.01 changes, so 10 count changes, which is almost nothing. But when we deploy the booster plate at 25 degrees, we get the same kind of story of a change of about 0.02 in change in all the force coefficients. So this is about a 20 count change, which is again nothing, but it's a little bit more. So the actual forces seem to be unaffected by whether this wing is tilted to one side or the other, which is quite surprising. When you're going around a corner, I would have thought perhaps putting the wing at one angle, like tilting it one side to the other, would have a more of an effect, but here, not so much. So from these results, it can be concluded that the direct effect of tilting this wing really doesn't have much of an effect on the positive effect of, doesn't really have much of an effect on cornering. However, while it doesn't have a positive effect or a positive direct effect, it doesn't mean that it doesn't have an indirect effect. And interestingly, tilting the wing to one side and then the other changes the distribution of the downforce. In one configuration, there is more downforce over the rear axle, and the other configuration means that there's more downforce moving towards the front axle. So even though this isn't really a direct effect on the car's handling, there is an indirect effect, because when you change the distribution of the force on the car, the downforce, it changes the handling and the stability of it. So you could orient this wing so that you are increasing the stability of the car and the handling, so you can go around the corners faster. You don't have more traction, but you have a better balance to the car. So that could be beneficial in this particular case. So even though we don't have a positive direct effect, we could get a positive indirect effect. Now, let's move on to the gurney flap while cornering. I mentioned earlier what the gurney flap is and how it's so small. Figure 28 shows the effect of the gurney flap while cornering. To remind you again, this gurney flap is just a little flap that pops out on the wing, and is tiny, and it has considerable aerodynamic effects though. If you want to remember what they are, go back to our last podcast and listen to that again. In this podcast, we're going to be looking at its effects while cornering. So the gurney flap deployed increases the downforce during the cornering simulation by about 30 counts, which in this particular case is about an increase in the drag coefficient of about 7%. That's pretty damn impressive considering just how small this thing is. But let's look at the gurney flap when it also increases. But let's look at the gurney flap on the lift coefficient. So the lift coefficient also is benefited by the gurney flap. If we have the gurney flap deployed, we increase the downforce by about 4%, about 20 counts. So the gurney flap increases the drag by about 7%. It also increases the downforce by about 4%. In cornering, that's both good because we get more braking force. We also get more traction on the road. So the gurney flap is good for cornering as well. So gurney flaps are really kind of a miracle of aerodynamic engineering, and they're good. We can conclude that. So finally, sorry, I shouldn't say finally, we have a couple more things to cover, but in figure 29, we see the effects of the forces produced cornering compared to straight line cruising. So I would have thought that when we go around corners, the drag, lift, and side force reductions would be different to when we're going on straights. But that's not really the case. So we have this car cornering and going on the straights in a CFD, and the drag coefficient is pretty much the same. There might be like a 2% change between them in favor of the cornering. So the drag coefficient is a little bit smaller in the cornering, which is not great because you only have more drag there. But this is in a CFD configuration. I think that that's probably in the error still. The side force is not really affected much at all. And the downforce is really not affected too much either. Like you might say that the downforce is increasing by 2% in the cornering, which is good. But again, that could potentially be in the error of the CFD. So there's not really much of an effect when you corner compared to going in a straight line for a car, which for this car at least. So I'm a little bit surprised at that. I would have thought that there would have been a different overall like force on the car, but there isn't. So that's interesting. So that's the end of this podcast. We're going to leave it here. And in the third podcast in the series, we're going to go through the real world applications and real world testing. I was going to cover this in podcast number 2, but this one is already getting a little bit long and we don't have enough time, I don't think, to cover this real world testing in this podcast. So we're going to cover this in the third podcast. Just to recap what we looked at here, we looked at the effects of cornering compared to straight line riding on the car's drag, side force, and lift coefficient. We found that they didn't really have an effect, which is surprising to me. We also found that the only flap is really a gift from the gods, the aerodynamic gods on car aerodynamics. We found that in the last podcast and this podcast, it has very beneficial effects in the cornering. We have an increase in drag and an increase in the downforce. That's both sweet. We also found that the booster plate has a significant effect on the downforce produced on the car, which is quite nice, and it also increases the drag quite a lot. So that's also potentially a good thing to have on your car if you're racing. So that's in this video. Make sure to like, subscribe. And if you want to get better at CFD and or theory yourself, check out a course and links. And if you want to make your experiments 2 to 4% accurate, check out the Mr. Hawk. It's just we make to accurately measures the density of air. The reason why this is important is because the density of air changes by about 2 to 4% every day. So if you turn up to your wind tunnel in the morning and you do some experiments, you come back after lunch, you're going to be having different densities of air. That's a problem because now your experiments are going to be at different velocities in your wind tunnel. The Reynolds number is going to be different and everything, which means that when you try to find trends in your data, you're going to have a lot more errors and you're not really going to find accurate trends. What's more, if you try to use this data to validate your CFD, that's going to be a problem too, because the CFD is on a certain density of air and your experiments are with a different density of air. So that's not good. You're going to have obviously a mismatch in your data here and you can't really validate your CFD, which means that your CFD is going to be wrong as well. So that instrument gets rid of your experimental error there, and it also gets rid of the error between days, weeks, months, and seasons by getting rid of that like 10 to 15% error in the density. If you want to learn more about that, you can also see our website where we have a podcast dedicated to this topic. So you can find that in the link in the description. And I'll see you in the next podcast. Peace out, amigos.